All right, so let's head on to looking at this. All right, so ammonium carbonate here, we're looking at decomposition, and so nice to give us the chemical equation for the decomposition as well. So here we're looking for damp red litmus paper. So we have three products here. Of the three products, which one will interact with our damp red litmus paper? Carmen, maybe help me out with our first one over here. Ammonia. So what will ammonia gas do to our damp red litmus paper? Turn it blue. Okay, so we have three turn it blues, right? B, C, and D all turn blue. We either looking for bleach remains blue or then turns red. Joanne, what causes litmus paper to be bleached? Have you ever encountered this? This bleaching thing? Anyone? Okay, right. So this bleaching here is actually due to another kind of gas. So if you have not encountered before, then it's okay. We don't have to talk about it. But over here we are looking at. I think are you saying something? I see you unmuted. You don't hear anything. Oh no. I think you were trying to say something.
No, I wasn't. I accidentally unmuted myself. Sorry.
Awesome, no problem. Okay, hi, right. Okay, so here we are actually looking for turns blue and turns red. Why would it turn red later on? Why are we looking at the turns red later on? So turning blue. Go for the second one. Turning blue here, it's ammonia gas, right? So red paper will become blue because ammonia gas, right, as it dissolves into the water, and the damp paper, we have ammonium hydroxide, right? So that's going to be an alkaline, all right? Then this is where we have the turning red one. Okay, so we can see that we have both we have options for turn blue and turn red. One reason, of course, yes, right? The red one we cannot like turn red immediately, right? Okay, so that's what we're looking out for, right? But also because why does ammonia gas reach the paper before carbon dioxide gas does? Why would that happen? Why would the ammonia gas reach the paper earlier than the carbon dioxide gas would? Any answers? Any answers? You want to help me with this? Why would ammonia gas produced reach the litmus paper before the carbon dioxide gas would? Yes. 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 It's the MR. Ammonia gas, what's the MR of ammonia gas? Nitrogen is 14. So 17. Ammonia. Alright. So NH3 is 14 plus 3, that's 17. Carbon dioxide gas is 44. 12 plus 16 plus 16. That's 54. You do not need to memorize this. It's just that I keep saying so I know. Don't have to memorize one. You can always go to the periodic table and calculate, right? So 17 versus 44. 17, lower MR, faster rate of how do we describe this movement? Diffusion. Wonderful. Okay, so you will arrive at the paper first, causing that change first. Okay, that's it. That's a very straightforward question as an introduction here. Moving on, we're looking at ionization of H3PO4. Do you know the name of H3PO4 is? Phosphoric acid. Actually, I just saw it right there in your paper just now as well. It's the exact same question. Phosphoric acid here is a tribasic acid. Tribasic acid meaning when it dissolves in water, it releases 3 hydrogen ions per H3PO4 molecule. Okay, simple as that. We're looking for ionization, meaning every time it splits, it is a 1 hydrogen ion at a time. So to do this question, actually, the best way is to write out your 3 ionic equations. Your equations for the release of the H plus. Okay, right? Carmen, this one you chose. Which one cannot be formed? I hope you saw the question correctly. Which one is the incorrect statement? B is correct, and therefore you are correct. B is the correct answer, right? I will not have HPO4 minus. Okay, so please note that, all right, in PO4 by itself, PO4 is like that. Okay, so if you look at part B, HPO4, that would be incorrect because if there's a PO4, it'll be a 3 minus. If you only have one H plus, it will be HPO4 2 minus. So do we see that B and C are mutually exclusive? B and C are mutually exclusive, that cannot occur at all. Can? Okay, so think of the chemical equations for the dissociation. Okay, the dissociation is very important. Awesome. Answer is B. Okay. Wait, what happened? Okay. What happened to my son? Okay. All right. So we're looking at electrical conductivity. What does it mean to be able to conduct electricity? Kaitong? What must something have to be able to conduct electricity? Is it just ions? Is it just mobile ions? Can I have something else that can conduct electricity as well? Mobile something else. If it's a solid metal, I have ions, but they are not mobile. So what is a mobile thing in the solid metal? Electrons. Wonderful. Okay, so together, all right, they are going to be referred to as a mobile charge carriers. As long as you are a charged particle and you can move, you can conduct electricity already. Okay, so what we are looking at here is sulfuric acid added to this alkali. We have the decrease in electrical conductivity. So if just now Kaitong reminded us that, hey, I need to have mobile charge carriers to be able to conduct electricity. If my electrical conductivity very high, means I have a lot of mobile charge carriers, correct? Then if it decreases, means I have less and less mobile charge carriers. We are looking at why will I have less mobile charge carriers now? Why will I have less mobile charge carriers here? Okay, so here we are looking for sulfuric acid and an alkali. We are thinking of an equation that will result in a decrease in the number of or the concentration of mobile charge carriers here. Okay, so Yumi, share with me your answer questions, please. What do you put? Never put. Why? What challenged you? What challenged you? Do you think of the mobile charge carriers thing? Do you understand what I'm saying now? To be able to conduct, I must have something that can move and is charged. Correct now. Okay. Sulfuric acid, obviously got mobile charge carriers now because you dissolve in water, you will have your H plus and your sulfates. Okay. What can I add to sulfuric acid, right? They will remove them. They will remove them. So here, all four hydroxides, I will have neutralization reactions. Very straightforward. Okay. What are the products of neutralization? That's it, just salt and water only. Very straightforward. Okay. So let's say, for example, sodium hydroxide. Sodium hydroxide is sulfuric acid. What are the products? If you're not able to visualize, then write down. Sodium hydroxide and sulfuric acid. Shannon, products. Sodium hydroxide, sulfuric acid. The salt is Na2SO4. Oh. Right? Okay. So sodium sulfate and water. So is sodium sulfate soluble? Sodium sulfate soluble? Yes. All sodiums are soluble. So if it's soluble, means you will have ions, and in water, then it can move, right? So the electrical conductivity will remain high. That is how you can think about this question. Okay, so I must therefore be looking for something the reaction will produce insoluble stuff, and they will no longer be mobile. So Joanne, question 3 you chose. Can you tell me what the product is? Barium sulfate is insoluble. Awesome. So sulfuric acid has a lot of mobile ions, H plus and sulfates. As you add barium hydroxide, the product is barium sulfate, which is insoluble and is neither mobile nor charged. It remains as your ionic compounds that are bound together in a solid state there. So you will actually have a precipitation over here. Okay, and that will reduce the number of mobile charge carriers, therefore reducing electrical conductivity, eventually until completion. Therefore, no more mobile charge carriers, no more mobile ions, and I have no electrical conductivity. Okay, so answer here is A, barium hydroxide. You mean following? The face says no. Which part are you still stuck on? Yeah. So honest, thank you. Okay. All right. So here, all right, we are looking at the some elements present in on Earth, right? Okay. And which one gives me the correct number of each of the oxide? So I have 4 of them over here. Pretty straightforward over here. This one, how this one, you really just must remember one, eh? Okay, so you have your Metal oxides versus non-metal oxides. Joanne, can you help me out with this first? Non-metal oxides are non-metal oxides. Which one? Non-metal oxides. No, as in of these four, they fall under no. Okay. Non-metal oxide, metal oxide. Alright, so this is how I remind myself as well. Okay. So neutral are also the Joanne, you were saying neutral also contain my non-metal oxides, right? Alright, but over here I'm just gonna put a little small fine print some. Alright. So what are some examples carbon of neutral oxides? What else? Anything else? Okay, so these are the three. Just very simply put, we can remind ourselves: dihydrogen oxide, carbon monoxide, nitrogen monoxide. Okay, so just remind ourselves. You memorize the neutral and amphoterics. Acidic and basics is just all of the others. Make sense? Okay, instead of trying to memorize every single all four columns, just remember neutral and amphoteric. Then everything that is neither of those fall under acidic and basic. Can? Okay, so a very common amphoteric oxide. Share an example, please. Zinc oxide, what else? Lead 2 oxide. And one more, the most obvious one. Aluminum oxide. Okay, so actually, personally, I would say that this one is the most common. Aluminum oxide is the one that's the most common, the amphoteric oxide. Okay, if you need help understanding what an amphoteric oxide is, you think of the word amph, then we think of an amphibian as well. Right, amphibians like both land and water. So similarly, amphoteric oxides can react as can play the role of an acid and an alkali as well. Right, so maybe that will help you understand the word amphoteric a little bit better. Amphoteric amphibian, if amphibians like land and water, amphoteric oxides can adopt the role of both an acid and an alkali when reacting with the opposite. So if I place aluminum oxide with an acid, aluminum oxide will take up the function of an alkali and vice versa. Okay, right, so this one fairly straightforward. With this in mind, question 4, how many you chose? B for Bravo, you are correct. Okay, fairly straightforward. So remember the last two columns, 3, 3, everything else is acidic and basic really. Okay, excellent. Now let's have a look at our pH curve, and understanding all our titration curves as well. Okay. So looking at the language, right? So oftentimes not just understanding the concept, remembering the points, we need to understand language as well. So when the language says titrated with aqueous potassium hydroxide, have you all done titrations yet? All right, what are the two apparatus we use? The one that is clamped onto the retort stand is the burette, and then the one on the table, you mean is the one that is clamped on the retort stand is the burette. Yes, the one that you swirl, the one that has this triangle shape, the thing. What kind of a flask is it? Yes, conical flask. Because you said pipette, I was like, yeah, I was ready. Hiya. Okay, all right, so if formic acid is titrated with aqueous potassium hydroxide, who is in the conical flask? Who is in the burette? Formic acid is titrated with aqueous potassium hydroxide. Which one is in the burette? Which one is in the conical flask? Very good. Okay, if I titrate A with B means I'm adding B to A. You understand that? If I titrate, the formic acid is titrated with aqueous potassium hydroxide. Formic acid, I add aqueous potassium hydroxide. So I add the burette, I do so. Okay, so understanding the language there. So therefore, this graph here, so nice. Okay, they already tell us the answer already. Okay, so what we're looking at over here is I'm going to be adding potassium hydroxide. So adding potassium hydroxide is like that. Okay, so if this one over here, we're looking at formic acid, acidic, so that's definitely have to be below 7. Are we looking at a very near 7 or very far away from 7? Here, they give us this really. So if it's weak acid, we would expect the pH to be super low, isn't it? All right, it's gonna be pretty close to 7, but still below 7. Okay, so we are looking at either A or D. So between A and D, Kai Tong, your answer would be D. Why D? Okay, so potassium hydroxide. Okay, we know that formic acid is a weak acid, isn't it? How would we describe the property of potassium hydroxide then? Strong or weak? Potassium hydroxide, this one no doubt on it's just strong. Yeah, okay. Your potassium, sodium, all these hydroxide, all these very, very common hydroxides, right, are strong. Are strong alkalis. Okay. So when I have a weak acid and a strong alkali, what would my endpoint be? Where would my endpoint be? My endpoint will be closer to the strong one. So if it's strong, then middle 7 lah. Okay, so if I have one strong, one weak, my change in pH, my endpoint will be closer to the stronger thing. So if I have a weak acid, strong base, my endpoint is nearer to the stronger base. If it's the opposite, where I have a weak base, strong acid, my endpoint nearer to the strong thing, which is a strong acid. So over here, my endpoint has to be nearer to the strong base, and therefore answer is A. Does it make sense? Do you understand that? Another clue that we can see is my NPH, my final pH. Look at that, my final pH. If you know that aqueous sodium hydroxide is strong base, I should be at 14. Versus this one, oh, weak leh. I don't convince you this. You see why answer should be A and not D, huh? Awesome. Can? You mean why you stuck with? Come, you must tell me what you don't know, then I can help you know. And okay? Awesome. All right. Friends at home, if you have any dying questions, please let me know as well. Okay, moving on. Question 6. Still about sodium hydroxide. Still about sodium hydroxide. And then I have an aqueous solution here, blah, blah. This is nearing towards QA already, right? Okay, nearing towards QA and a little bit of salt already. I have white PPT that dissolves with excess reagent. This is our cation test, isn't it? What forms a white PPT that disappears in excess? Sodium hydroxide. What are my options? You must remember, aluminium, lead, and zinc. You all learn QA already? Do you have your QA notes? Anyone brought your QA stuff? Or qualitative analysis? Then could you all do this question? Okay, skip. Okay. Okay, skip. Wait, skip. Salts. Then this one you also cannot do what? The one they all start on 7 just now. Yeah. Okay, skip. Okay, but 8 can. 8 is salts, isn't it? Okay, 8 can. Okay, apologies. 6 and 7 is your QA. Forget about QA. Okay, come. Question 8 here. This one definitely should be able to do. This salt preparation. So what are the 3 properties that we need to keep in mind when we're talking about salt prep? Solubility, thank you. Okay, so over here, if I want to make calcium sulfate, is it soluble? So think of a solubility table. All sulfates are soluble except for calcium. Sorry, lead and barium, right? Calcium, barium, lead, sulfates are insoluble. So definitely I'm just jumping straight into precipitation. When I want to use precipitation, what are the properties of my reagents? If I want to make something insoluble, I'm going to start with 2 soluble things. Right? So our answer should be looking for 2 soluble things. Okay, so we should have chosen C. Come on, what you choose? Never do? Cannot figure out. Shannon, you chose? Kai don't come share me your answer, please. Let me work on it. You put B. Calcium metal to sulfuric acid. Okay. Here, this question say now the question doesn't say which method can prepare. The question says which is the most suitable. Acid metal reactions, you quite not. So like theoretically cannot. Yes. Practically, realistically, should we do it? No. So it's not a suitable method. Right? So that's why you must understand the wording. Suitable method doesn't mean can it work. Acid metal can, but it's not a suitable method. Understand? Okay? What was that? What was that? Yeah, reactivity series, reactivity series. Okay. All right. So answer is definitely going to be C. I'm gonna use a neutralization reaction. Simple as that. Okay, neutralization reaction. Then I have to filter. Do yeah, okay, I filter it. Can? Okay. All right. So simply put, I'm just gonna get my precipitate to this reaction. Okay. Filtrate is the one that flows through. Then the one that remains of filter paper is this one is your separation techniques. Residue, very good. Okay, residue remains, filtrate flows through. Okay, so let's keep that in mind. Can? Acid, filtrate. I think, are we adding to residue? So we're looking at calcium sulfate, calcium nitrate. Oh, yeah, then it's a displacement reaction in the second step. The first step, calcium hydroxide, dilute nitric acid, I'll get calcium nitrate, right? Calcium nitrate, I add sulfuric acid, then I displace to get calcium sulfate. Is it? Okay, write down. Come, let's write down. Okay? Come. That's good, that's good. Come, let's work on this. Calcium hydroxide plus nitric acid. What do I get over here? What's my salt? What's my salt? And then water. So, Joanne, are you saying that calcium nitrate? What is the property of calcium nitrate? So everything will flow through, Oh, wow. Can see not? Both. So when I filter this, the end product, everything will flow through. Yes. Okay, what's the point of filtering? Here, we are looking at calcium hydroxide. Sometimes is sparingly soluble. So if you do have solid particles left inside there, I do not want it. I want to ensure I get only my calcium nitrate. Then later on, my calcium nitrate, I will have my displacement reaction. I will swap partners. So I get back. Excellent question, isn't it? Right? Right, so we really must be comfortable with drawing our equations. Be comfortable with drawing our equations. Okay. Awesome. All right, come. Let's quickly jump through. We are not going to work on every single question here. We're just going to jump ahead so that we can work on the next set as well. And not to worry, I'll pass you all the answers later on as well. So let's work on this quickly with me here. Difference between strong and weak acid or alkalis. We're looking at the degree of dissociation, isn't it? Degree of dissociation. Okay, so you mean strong acid versus weak acid? They're just cheering you on. Come on, yes. Okay, and then weak acids will? partial, right? So complete versus partial dissociation. If it's acids, it's H plus. If it's alkalis, we're looking at OH minuses. Okay. So this is our titration curve. Based on this, it's just a straight line there. So it's just missing the printing. So let's put the straight line out there for me, please. This one. Yeah. Okay. All right. So you all have all done mole calculation? Learn how to do mole, eh? Okay. Okay. Then also just keep. Okay. Here is definitely doable then. Okay. So you're picking your appropriate indicator. Which one can we use for this particular reaction? So look at your endpoint. Shannon, you will choose. Yes, gonna pronounce that right. Yes, pronounce. Which indicator will you choose? And what is that called? Okay, phenolphthalein. Okay, phenolphthalein. All right, phenolphthalein is our correct indicator because my endpoint is pH 9 and which is right smack in the middle over here. Okay, phenolphthalein. Phenolphthalein. Okay. Science, yeah, next time they ask you, you want make account here and there, as you make password, right? Use all this. No other people will know one. Phenolphthalein, then the L just one there. Okay, nobody can hack your account, right? Okay, all right. All right, so definitely it's phenolphthalein. We're looking for the endpoint within the color change range. Okay, let's move on. Okay, so typical of a kind of like a application question where they give you a whole chunk of information that is not necessarily in your syllabus. Okay, so let me walk through this with you. So a halide, think of halogens. So that is going to be hydrogen halide is just HF or HBr or HCl. Your fluorine, bromine, chlorines, all these are halogens. You all know what are halogens? Encountered before? What's like never do halo? Never hear this word before, man. Okay, this one is group 7. This one, I'm pretty sure you know what group 7 is, right? Periodic table group 7. All those in group 7 are known as your halogens. So halides, as you can see in the table below, we have a HF, hydrogen fluoride, hydrogen chloride, hydrogen bromide, and what is high? Iodide, thank you. Okay, so when dissolved in water, now look at this, when dissolved in water, this is our application portion. Okay, they're gonna form acids. Yes. V is 5. So therefore, yes. Okay, if you look at periodic table, it's also there, right? Okay. All right. So 17. Okay, in that thing is 17. Yes, that thing is 17. Okay, but usually we will ignore the entire middle thing. Okay. Okay, so here we do not need to calculate. This one they are giving it to you as an application question. We're looking at pKa, right? The smaller the pKa, the greater the extent of dissociation. So stronger acid. Application question, that's just it. The only thing you need to know about pKa is this measure of the extent of dissociation. The smaller the pKa value, the stronger the acid. Okay, that's all you need to know about pKa for this question. Okay. What is the trend between bond energy and the pKa values? Is there a relationship there? So from F to Cl to Br to iodide, we have 562 decreases all the way down to 299. Correct? So this one decreases, then pKa also decreases, right? Do we see a relationship here? Right? So if the bond energy decreases, what is bond energy? Bond energy is the amount of break the bond. Bond energy is the amount of energy I need to break that particular bond between the H and the X. The higher the bond energy, the more difficult it is to break, right? So do they dissociate as easily? No, that's it. So you have it already. So if my bond energy is 562, I need a lot of energy to break. My pKa is high. High pKa means weaker acid. Okay, no worries. Okay, because they want to stay together. Correct or not? They will rather stay together. That's why the bond energy is so high. Okay, so we are looking at how this bond energy relates to pKa, relates to acid strength. Okay, relates to acid strength. Okay. So what we just did over here is just 2 and 3 lah, right? Just 2 and 3 over here. So we're looking at the trends over here. The greater the bond energy, the more the H and the X want to stay together. How to form the ionic? Split. Yes. Split what? What do I split? All the aqueous. Excellent. Go ahead. Then those non-aqueous one, how? Leave it. Leave it means leave it up there, or do I bring it down? I still bring it down. Very good. Then what do I cancel out? What do I call those? Spectator ions. Excellent. Okay. They don't kill lah. Chemistry only. Yeah, lor. No lah. Hey, okay. Come. Let's split together. Aqueous, I split. What's gonna happen is I have my Na plus. Wait, is it balanced? Balance? Yeah. Yes. Okay, so balance here, I can leave it. Okay, Na plus OH minus plus X minus. Okay, this is everything on the left side already. How? That's all. Then this side. Yeah, Na plus again. Okay, then cancel sodium and X. Then so my answer is actually just six, 3, 7, 5, 4, 5. 6, 3, 7, 5, 4, 5. Okay, let me tell you right now, no matter what acid or alkali, the ionic equation is always the same. So, next time you all see any random acid or any random alkali, they ask you to do ionic equation. Do you have to go through the entire set? The entire process? Don't need. As long as it's an acid and alkali, ionic equation is always this. Understand? Understand what I'm saying? So next time you all see a question asked for ionic equation, next time you all see a question asked for ionic equation for acid and alkali also neutralization reaction, right? Just write this one. That's it. Okay, so this is a hack for y'all, okay? All right. What? What are you asking? Is that a yes or no? Yeah. Do you know why not? What is the thing that reacts in the acid is the H plus? What's the thing that reacts in the alkali is OH minus? So H plus OH minus water. That's it. Okay? Ionic equations for neutralization reaction is always the same. Okay? Okay, Shannon, was that an actual eureka moment? Okay, come, let's move on. Dissociation equation. What should be shown in the dissociation equation? What is dissociation? So what is dissociation first? When the molecule dissociate to form. Yeah, that's it. So draw that. That's all. Like that. What is missing there? In an equation? You don't. Yes, the arrow. Yes. But I cannot do this. Why? What's that called? Reversible arrow. Why must I put a reversible arrow over there? Because, sorry, I heard it. Weak. Very good. So, weak acid and alkali dissociation must put reversible arrow. Whereas strong acid, strong alkali dissociating, then we put a single arrow. Oh. Can okay. And we're not gonna write down for part 2. Can you just tell me, will it have the same pH as hydrochloric acid? Why? Who has a lower pH? Hydrochloric. Okay. Hydrochloric, stronger acid, lower pH. That's it. Okay. Hydrofluoric, weaker acid, higher pH. But still will be below 7. Can? Okay. Awesome. Okay. So skip 3. Skip 3 is QA. It's QA. It's, okay, that's all. Come, let's go. The other two questions are QA already. No, we can see that. Q and 1 of G. Okay. All right, ladies at home, we are moving on to the next set. We are looking at Ken bonding ion equations now. Ken bonding ion equations now. And if you know any friends that were in the Zoom just now and we have lost them now, please share with them the link. Okay? Yeah. Okay. Come, dot and cross, dot and cross. Can I confirm that chemical bonding and ionic equation both are specifically coming up in your weighted assessment? Okay, okay. You know what did I say? You hear, but your ears like not here, leh. Sharon, come.
Yeah, no.
Ah. Okay, so I have yx3, yx4 and a z. Wow, okay, I tell you, in our syllabus, there's only one thing that looks like yx4 plus. Can you tell me that? Look at this. This is yx4 plus. There's only one thing on syllabus that is yx4 plus. 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 PO4, 3 minus. What is something 4 plus? What? Wrong, but very close. Medium. Oh, yeah, you said. Oh, I couldn't hear you. I never say wrong. I just asked you to repeat. You repeat the wrong thing. Okay, right. So this, just tell yourself, this is it. So what we're looking at over here is yx4 plus. Okay, so in your syllabus, it's very likely that this is going to be ammonium already. Okay, I'm telling you that it's likely only. So this helps you to jump through some steps a little bit better. But of course, we check first. Okay, so we can see that X only has 1 electron to itself, and then it shares 1 each with Y. Okay, so the hydrogen apply to X. So very likely this one is going to be ammonium, isn't it? Then what we look at Z, it has 7 of its own electrons, and then 1 taken from elsewhere. How do I know that 7 is from Z and then 1 taken from elsewhere, and not that it only has 1 and it took 7? Very good. It finds the easiest way. So it makes more sense to just take 1 than take 7, correct? And what's the charge over here? It is a single negative charge, meaning I took in a single negatively charged electron. Okay? And with that, So 1 electron in the outermost shell of X. That's all we say about hydrogen already. Okay. 5 in Y. Yeah, we talked about that as well already. Okay. So how do I know it's 5 in Y? I only got 1, 2, 3, and 4 over here. Why is it 5? Very good. We went to Z over here. Okay. So therefore, answer is D. 1, 2, and 3 are all correct. I thought which one do you think was the incorrect statement? 1. Next. Got 1 of it. This belongs to X. Correct lah. 1. Next one. Yeah. Okay. Okay, we understand now already? Can we clarify now? Okay. Thallium carbonate, Tl2, CO3. Sodium chloride, NaClO2. What is thallium chloride? How do I do this? Okay, both things I'm pretty sure are new to you, right? Thallium chloride, thallium carbonate and sodium chloride are both new to us, right? But within thallium carbonate, I know carbonate. Within sodium chloride, I know sodium. I use the things that I know to find out things that I don't know. So therefore, come, let's work on this with me, please. For this, I'm going to split it up. Carbonate, I know, CO3, 2 minus. And I need 2 thallium ions. What does that tell me about 1 thallium ion? Yeah, that's it. Tl plus. Okay? And then I do the same thing. Do the same thing for sodium chloride. I do not know what is a chloride, but I know the sodium. Na plus. I only need 1 chloride by itself. So therefore, this tells me that chloride minus. Question is asking us for thallium chloride, thallium. Answer is A4. Absolutely correct. Let's go. How are the 3 chlorides different? How are the 3 chlorides different? Any answer? How are the 3 chlorides different? I have magnesium chloride, aluminum chloride, silicon chloride. All these shapes, you all know already, right? It's in your syllabus, right? Chemical bonding, your giant covalent, giant molecular, simple molecular, ionic, all these kind of things. Is right. Okay. Right. Yes. What's the answer for this one? Question 3, fairly straightforward. It's just like a yes, no kind of thing. Number you choose. C for common, is it? How you choose? Everything C. Joanne, you chose? Why? Why is it C? Okay, very good. Why? Okay, very good. Right, answer is C over here. Diionic, simple molecular, simple molecular. Okay, C for common, C for correct. Very good. Okay, so they are just small molecules by themselves. Okay, fairly straightforward. So therefore, we are looking at their melting points as well. A very high melting point going to be ionic versus our simple molecular, relatively lower melting points. What brings the difference? What brings the difference? How do you explain the difference in the melting points over here? What am I breaking? What am I overcoming in a giant ionic compound to melt? Strong something forces of attraction. Yes, continue the word.
It forces
of attraction. Yes. Okay. So when I have to overcome the strong EFOA, I need a lot of energy. Melting point very high. Okay. In the two simple molecular ones, I'm not breaking the what bond? I'm not breaking the covalent bond. So what am I breaking instead? What am I overcoming instead? The very weak intermolecular forces of attraction. Okay. Right. So just keep that in mind. Similar question as question 2. I give you something that you don't know, but I top it up with something that you know. So using the same format I shared with you earlier on, can you try question 4? Tell me what's the answer. Think about the thallium and the chloride on question 2. And see if you can get phosphoric acid, you know? You know what's phosphoric acid? Phosphate is PO4. Hey, no, wait, I cannot tell you. You look at lithium phosphate. You know lithium or not? Periodic table. Yes. 1 plus or minus. Yeah. So if lithium is a plus, I need 3 lithiums. Phosphate is a 3 minus. Thank you. Antimony. Okay, no, the thing is, I don't put it down. You don't need to look at periodic table. It is there, but you don't need to. You know oxide what? Oxide, you must know what. You mean oxide is 2 minus. I need 2个 O. So means SB is what? No?
3.
Oh, no, yeah, correct. 2 plus. I saw wrongly. You mean brain faster than me. Very good. Okay. Okay, then you mean answer is? Absolutely correct. Okay, SB is 3 plus, PO4 is 3 minus, SB PO4. Yeah, that's why I say it. I haven't seen it on them. Where's SB? Okay. All right, awesome. Let's go. Question 5 is similar to question 3 to explain the melting point. Sharon, question 5. Why KCl low melting point than CaO? Why KCl lower than CaO? Why KCl lower than CaO? Yes. Excellent. Oh, later. Wait, no.
K plus and Cl minus, then it takes like less energy to overcome it.
Very good. K plus and Cl minus versus Ca2 plus and O2 minus. So it's a greater force of attraction in CaO. Okay. Okay. Are you all able to answer the bonus question? You all got learn your VSPR? Do any of those words look familiar to you all? Answer is B. You all choose B. Oh, you all need to know B. Okay. Okay. Tetrahedral is central atom. 1, 2, 3, 4. Tetrahedral, 4 shapes. 4 tetra. 1, 2, 3, 4. So it's like that. Can you see that? Yeah. Okay. So, but you all don't know the others. That means not in syllabus. Never mind. Okay, let's move on stuff that are in syllabus. Okay, so this one is actually similar to what we discussed earlier on. Why sodium chloride, the melting point so high, 801. Then chlorine together is only negative 101. Super low. Explanation is structure and bonding. Question specifies structure and bonding. So we talk about both the structure and the bonding. So what is the structure of sodium chloride first? Very good, giant ionic structure or giant ionic lattice. Okay, what is the structure of chlorine? How do you describe the structure of chlorine? Very simple one. Yeah, simple molecular structure. Right, simple molecular structure. Okay, so with this, we're just looking at how their shapes over there, the structures over there. And then sodium chloride, very high melting point because like what Yumi mentioned just now, very strong EFOA, electrostatic forces of attraction. Okay, and whenever we talk about EFOA, you must tell me between what and what. So within sodium chloride, the EFOA is between. Okay, so sodium cation, chloride anion, right? You cannot just sodium and chlorine. Okay, you must talk about the oppositely charged particles. Okay, and then we talk about what is found in chlorine. Do we talk about the covalent bonds between chlorine atoms? We talk about the weaker intermolecular forces of attraction, right? So right up to this point, we have 3 marks already. We talk about the two structures. We talk about what is in sodium chloride. We talk about what is in chlorine. Where is our 4th mark? Compare what? I already stated structure already, ma. I already compared structure here. Right? Yes, the energy. Very good. So our 4th marking point, a lot of energy needed to overcome strong EFOA, high melting point. Very little energy required to overcome weak intermolecular forces of attraction, low melting point. Following, common eye following.
Is it like one sentence say like
So you can just give me 4 sentences, very straightforward.
say like sodium chloride and chlorine compare in every sentence or like
Okay, so first sentence is structure of sodium chloride and chlorine. Second sentence is what is the force I'm looking at in sodium chloride? Third sentence, what force in sodium? Fourth sentence, energy. Can? Okay. All right. So let's just try and understand first. I'll pass you the answer key later on. No worries. Right. Just try and understand what I'm looking at first. Okay. Electrical conductivity is something we talked about earlier on, isn't it? Electrical conductivity. Why sodium chloride can conduct in molten, but not in solid. Molten means what? Liquid state. And if it's in liquid state, the particles can move. Then to conduct electricity must have
I don't know, mobile.
mobile charge particles, right? Charge carriers. Then you have your ions that are mobile lah. You only use of electrons in metals. Can? Okay, so only in the molten state, the sodium cation and the chloride anions can move around because in liquid state. Okay, but if in the solid state, they are all stuck in their fixed positions. That one's for metals. This is not metal.
Yeah.
Yeah, yes. Okay, and okay, so this one is a repeat of what we are doing. This is a repeat of what we're doing. See, we only have time for one more thing, right? Okay, y'all. In your own time, y'all see question 8. Question 8 is about VSCP. I thought y'all learned already. Never mind. Question 8 is not in your syllabus, so just skip question 8. Okay. I want to jump ahead to ionic equations since we kind of like struggled earlier on. But we only have like 2 minutes, okay? Okay, what did I say just now about neutralization and ionic equations? What did I say just now about neutralization and ionic equations? It's always the same. What is it?
OH minus equals H2O.
Equals.
Like give you H2O.
Yeah, okay, produce H2O, that's it. Okay, so neutralization, no need to do it. It's just that. Okay, no need to do it, Okay. Let us just do one thing. Never learn displacement, meh?
No. I've never heard the term.
Never heard the term before. Okay, then am I very good. Then we are done with it. Let's look at these two equations. Let's look at these two equations. Lead nitrate and ammonium chloride. I purposely leave space over there so you can use our workings. So we're just going to do lead nitrate and ammonium chloride. Do you all know what is the formula of lead nitrate first? What is lead nitrate? Tell me. Formula of lead nitrate. PB? Is it just like that? Okay. This one error. Let me add in, please. So that means what? Okay? Lead 2 nitrate, meaning I have Pb2 plus. So therefore, I need 2 nitrates. Okay? And then I have ammonium chloride. Oh, what's the state of this? Lead 2 nitrate. Nitrates. All nitrates are soluble. Full stop. Okay? Come, next one. Ammonium chloride. What's the formula? Chloride is? So just Cl. That's all. Alright now. Okay? Soluble or not? All ammoniums are. Come, what do I get? What do I get? Ammonium nitrate, very good. Plus? Very good. Hi Tom, you see this is lead nitrate, this is ammonium chloride. I will just swap partners. Lead nitrate now is lead nitrate. You see I swap partners. Okay, so swap partners only. Okay, so this is my chemical equation, but have I balanced it? Lead 2 ma. What was your question? What if you put PbNO3 here? Sorry? Okay. PbNH4. Pb is a cation, NH4 is also a cation. Yes, always. Okay. Come, this is the final thing we do together today. Let's go, let's go. Balance this equation for me, please. Two where? I put a two where? Very good. Now, I made an error. Lead chloride is insoluble. All chlorides are insoluble. Except for super lead. Oh, so chlorides are soluble except for silver lead. This is lead. Yes. Okay. Okay. So do our split. We have Pb2 plus. Okay, over here, look at this. I have 2 nitrates over here. When I split into my ions, I must have 2 nitrates. Okay, I must have 2 nitrates. Again, I balanced earlier on already. So I need to have 2 ammoniums and 2 chlorides, giving me 2 ammoniums again and 2 nitrates. And I will just bring down my Shannon. You mean my next step, please? Tell me what to cross out, please. Anything else? Awesome. So my final answer, fairly straightforward. I write down my lead 2, Arthur and Joanne, are we on the same page? Can you get the equation? Okay, so okay, I saw the time we have over here. When is your paper? Okay, still got time, right? So in the next few days, right, go and do up the other questions that we have left blank there. I will pass you all the answers in the next few days, and then you all can check it out on your own. Okay, then thereafter, right, think about it. If you do wish to start a class together, just drop me a text on WhatsApp and we can continue to discuss all this. Okay, if not, all the best for your revision, and yeah, I'll see you next time then. Okay, so all the best, don't die, chemistry can one. Okay, all right. So if you are staying for bio, then just stay. Then I will move on. For those online, if you are staying for bio, please do stay as well. But if not, I will see you next time.